You know, it's kind of crazy to think that just 15 years ago, AI was this niche thing, mostly stuck in academic labs. Now, it's literally changing the world. But how did we get here? What was the recipe, the secret sauce that took us from simple computer programs to the powerful AI we have today? Well, we're going to unpack that whole journey. Let's dive in. Seriously, think about this for a second. How on earth did we get from teaching a computer to find a cat in a random YouTube video to building a system that can solve math problems from the International Mathematical Olympiad? I mean, these are problems designed to stump the most brilliant human minds. That's the incredible leap we're going to talk about. And a great guide for this story is Google's chief scientist, Jeff Dean. See, back when he was in college in 1990, he had this idea to get brain-like computer models, neural nets, to learn using just 32 processors. But as he said himself, he was completely wrong. It turned out the first key ingredient wasn't a fancier algorithm. It was scale, a mind-boggling amount of computer power, like 1,000,000 times more than he first thought. Right, so that leads us perfectly into our first big idea, the dream of scale. Because before AI could get any smarter, it had to get bigger, a lot bigger. I mean, just look at this leap. In 1990, we're talking about a college thesis project with 32 processors. You fast forward about 2 decades, and the entire goal of the new Google Brain project was to train massive neural networks. And they weren't messing around. A year later, they were training models that were 50 to 100 times bigger than anything that existed before, using thousands of computers. The dream was finally becoming real. So, how in the world do you train a model that big? The answer was something called unsupervised learning. Think of it this way. Instead of spoon-feeding a model millions of pictures with the label cat, you just don't. You show it billions of random pictures from the internet, and you force it to find the patterns on its own. It's learning by watching, not by being told what to look for. And this is where the magic happened, the famous cat paper. The team just let their giant model loose on 10 million random frames from YouTube videos. And guess what? With zero human help, no labels, nothing, it figured out the concept of a cat all by itself. This was the big aha moment. It was proof that massive scale, combined with this unsupervised learning idea, that was the path forward. All right, so the concept was proven. Scale works. Now what? The next challenge was to take that power and use it to understand really complex stuff, like human language and all the images we see. So the big breakthrough here was to stop thinking about words as, well, just words. Instead, they started representing them as coordinates in a huge multi-dimensional space. We call these vectors. And by turning words into numbers, the models could suddenly do math on meaning. You've probably heard the famous example. If you take the vector for king, subtract the vector for man, and add the vector for woman, you land right next to the vector for queen. It's incredible, right? The models were starting to understand the meaning behind the words. But with great power comes a great big problem. Jeff Dean did the math, and he realized that if they wanted to roll out a really good speech recognition model for everyone, they would literally have to double the number of computers in all of Google's data centers. No way. They had hit a massive computational wall. The old way wasn't going to cut it. So what do you do when you hit a wall? You build the door, or in this case, a whole new kind of chip. Google developed what they called the Tensor Processing Unit, or TPU. These things were custom-built just for AI, and they were beasts, 15 to 30 times faster and up to 80 times more power efficient. This wasn't just an improvement, it was a revolution. It broke the bottleneck and suddenly made AI at a global scale actually possible. Okay, so we've got the muscle, the raw power. We've got the custom hardware to run it. But the next ingredient? Oh man, this one was a true game changer. This is when a new model design came along and just changed everything. It was called the transformer, and its secret sauce was a mechanism called attention. Now, instead of reading a sentence one word at a time, like you and I do, the model could look at or attend to the entire sentence at once. It could see how every single word related to every other word all at the same time. This gave it a grasp of context and nuance that was just impossible before. And the results were just jaw-dropping. The research paper that introduced it was titled "Attention is All You Need." And they weren't kidding. These new transformer models were more accurate while using 10 to 100 times less computer power. It was a quantum leap in efficiency. This new architecture also unlocked a super clever way to train models called self-supervised learning. The best way to think about it is like playing the biggest game of Mad Libs in history with the entire internet as your playbook. You just show the model a sentence with a word blanked out, and its job is to guess the missing word. By doing that billions and billions of times, it learns everything: grammar, facts, relationships, and even the early hints of reasoning. Okay, so the foundation is set. We have this incredible transformer architecture. Now the game shifts. It's not just about making models bigger anymore, it's about making them smarter. It's about teaching them how to actually reason. One of the key innovations here was moving to what are called sparse models. Before, the entire AI model would light up for every single question. Super inefficient. With sparse models, only a tiny fraction of specialized, expert parts of the model activate for any given problem. It's kind of like our own brains, right? You don't use every single neuron to tie your shoes. This efficiency lets us build vastly more powerful models, like Gemini. And then there's this other trick that sounds almost too simple to work, but it's incredibly powerful. It's called chain of thought prompting. Basically, instead of just asking for an answer, you show the model how to get there. You give it an example and say, here's how you solve this, step by step. You teach it to show its work. And by doing that, it suddenly gets way better at solving complex problems. But hold on, these giant models are, well, they're giant, they're expensive. You can't stick one on your phone, right? Well, that's where this cool idea called knowledge distillation comes in. You use a huge, powerful teacher model to train a much smaller student model. And the teacher doesn't just grade the student's answers. It passes on its whole thought process, its intuition. It's basically an AI mentor. And get this, the results are just mind-blowing. A student model can learn to perform at over 95% of its massive teacher's level, but using just a tiny fraction of the data. This is how we get that incredible AI power into the devices we use every day. Okay, so the last piece of the puzzle, the final polish, is fine-tuning. This is done with something called reinforcement learning. It's basically a reward system. Humans can rate the AI's answers, giving it a thumbs up for being helpful and safe. Other AIs can act as judges, and in some cases, the real world is the judge. If the AI writes computer code, it gets a reward only if the code actually works. This whole feedback loop is what helps steer the AI to be genuinely useful. All right, so let's take a step back and look at the whole recipe. You start with massive scale. You build custom hardware like TPUs to power it. You use the revolutionary transformer architecture as your foundation. Then you sprinkle in clever techniques like sparsity, chain of thought, and distillation. You put all that together, and what you get is the current generation of AI, models like Gemini. And that brings us full circle, right back to where we started. The ultimate test of this new reasoning ability? A problem from the International Mathematical Olympiad. And remember, just a couple of years ago, in 2022, these models were struggling with middle school math. We're not talking about your high school algebra test. We're talking about problems designed to stump the brightest young minds on the planet. So how did it do? Well, here's Jeff Dean with the punchline. We solved 5 of the 6 IMO problems, which gets you a gold medal. Wow. In just 2 years, AI went from struggling with basic math to achieving gold medal performance at one of the hardest math competitions in the world. That's the power of this recipe we've been talking about. And so that's the journey. The models are here, and they are incredibly capable, which leaves us with the biggest, most important question of all. The question for all of us now is, how do we make sure this powerful reasoning is used for good? How do we channel it to unlock amazing benefits for science and education while being really thoughtful about managing the risks? That is the great challenge and the incredible opportunity that's right in front of us. Thanks for coming along for the ride.